My name is Pimbi. This is a demo presentation of Cloud 3, Texas Tech University EC Department with Dr. Helm. This project is to design and engineer AM SSB CW receiver. The project description: design and engineer AM SSB CW receiver uses product detector capable of receiving signals within the 6-meter emitter radio band from 50 to 54 MHz. The system has an input sensitivity of 10 dB, signal to noise and distortion ratio at minus 90 dBm. The system has an AJC dynamic range of at least 30 dB and has 20 dB of manual selectable input signal attenuation. The input impedance of the system is 50 ohms non-reactive, and the output drives an 8 ohm speaker and capable of delivering at least 100 milliwatts of audio output with less than 5% of total harmonic distortion. This is the main block diagram of the entire system, and we start with the antenna, which is simply a conductor, and when it is exposed to radio waves, the waves induce a very small alternating current into the antenna to produce the AM signal at the input of the RF amplifier. This RF is a very sensitive amplifier that provides an amplification for the very weak radio frequency signal captured by the antenna. And it needs to be mentioned that between the antenna and the RF amplifier, there is two important circuits: the selective attenuator and a low pass filter. The output of the RF amplifier is then passed to the mixer and the local oscillator, which translates the frequency of the incoming signal to the IF frequency. And the IF frequency is going to turn the IF amplifier on. And we have the AJC, which adjusts and controls the gain of this IF amplifier. And the reason why of this AJC feedback is to provide a great amplification for the very weak signal received by the IF amplifier. The output of the IF amplifier is then passed to the product detector, where demodulation finally occurs to produce an audio signal. And we have a bit frequency oscillator, and the reason why we have it is to overcome the difficulty to hear the CW signal on a normal receiver. The output of the product detector, which is an audio signal, is then amplified by the AF amplifier and then sent to the speaker so that we can hear the message received. This is the RF amplifier. So I'm gonna run each module by itself because of the running time in LT Spice. For this RF amplifier, the input signal should come from the antenna. So here in LT Spice, so we are able to generate that signal using a carrier and the message signal. So the carrier is at 50 meg, and then the message signal is out 1 meg. And the mix of the two signal give us a signal which is similar to what the antenna should send to the RF amplifier if this circuit is implemented into hardware. So this signal, which is similar to what the antenna should send to the RF amplifier, so this is what we use as input signal to this entire circuit. So I need to mention that we did not include the selective attenuator because that one is a network of resistors, but we have this band pass filter which passes signals with frequency between 50 and 54 meg, and the output of this band pass filter is sent to the actual RF amplifier, which is a 2 stages amplifier, and this amplifier is supplied by a 12-volt battery, and this is based on the project description, and the outputs is taken at the collector of the second transistor, and we have a transformer, and the actual final output of the RF is taken at the output of the transformer. So I'm gonna run it, and we're gonna see the input and the output signal, and see how the RF amplifier is gonna behave in LT Spice. So I'll go ahead. So let me run it. Here we go. So yeah, it's running, taking a couple times. Okay. So I'll go ahead and have the input signal. So this is the input signal. Let me zoom in so we can see how it looks like. So if I zoom in here, here we go. Yeah, looking good. This is how the signal sent by the antenna to the RF should look like. Let me zoom in again so that we can see it's now it's looking better, way more better. So this is the input signal, and let me try to take now the output signal, which should be an amplification of the input signal. So the output signal is right here. So we have the output signal. Well, okay. So the output signal, so we can see the input signal right now because the output signal is simply an amplification of the input signal. So what I would do is delete this one. Yes, and plot back the input signal. Here we go. Sweet. Now we have the input and the output signal. We can see that, and the output signal is simply an amplification of the input signal, and we have the carrier frequency as well, the message frequency, which is at the top, as we can see, as well at the bottom. So this is the RF amplifier. This is the mixer, and we use a double balance mixer DBM with Schottky diodes, so the 4 Schottky diodes. And so the inputs of the mixer is, we have 2 inputs signal for the mixer. So we have the RF output signal, and so which is right here, and then we have the local oscillator output. So the mixer is the module or the block that multiply the 2 signal in order to translate the frequency of the RF signal to the RF frequency. So the output is gonna be here. So this is the output of the mixer. So as I mentioned, so we have the local oscillator. So the output is gonna come as input to the mixer, and the RF, so it's gonna come from the output of the RF amplifier. But here, since we don't have that output, so we did the same thing as we did into the schematic of the RF. So we generate a signal which is similar to what should be the output of the RF amplifier. So I'm gonna run it, and I know that this schematic really takes time to finish running, so I may speed up the process. So here we start running. So we have almost now 10%. So I'm gonna speed up the process. Okay, the simulation just finished running, and now I can go ahead and measure the signal, the input signal for the RF, and then LO output. So I'll start with the RF, so which is gonna be the mix of the two. So here we go. Yeah, so again, so it's gonna take time to run, so I'm gonna speed up the process. As you can see, so now we have the RF signal. So I'll go ahead now and run the local oscillator signal. So again, it's gonna take time, so I'm gonna speed up the process. So I decided to run the output by itself because it's really take time, and this is one of the reasons why I did not want to run all the module in one complete schematic. So because it's really taking time, but this is the output of the mixer, and as it turns out, so we don't have really a big uh, gain with this mixer. This is the local oscillator, and it is a cow-pitch oscillator, and so I'm not gonna spend too much time on it. So just to make sure that it's running, so I'll just take the outputs of the cow-pitch oscillator, and then so the output is right here, and so I need to run it. To run it. So here we go, it's running, and I can zoom in and 12. Yeah, so this is the output, and then I can go ahead and see the frequency spectrum. So here we go, so we have a nice frequency spectrum, and the frequency, so this frequency should be about 52 meg, should be about 52 meg. This is the IF amplifier, and it is a tone amplifier with a resonance frequency of about 455 kilohertz, and this resonance frequency can be found from C2 and L2, the primary inductor from this transformer. The inputs of this IF amplifier is simply the outputs of the mixer, and we have it by mixing the message signal of about 400 hertz and the carrier, which has the frequency of about the same with the resonance frequency of the IF amplifier. So the output is taken at the secondary of this transformer, and then we have the loads of 1K, which is supposed to be the inputs impedance of the product detector. So I'm gonna go ahead and run it, and I need to mention that so the IF amplifier, so it's gonna provide a gain voltage, and that's gain voltage is gonna be controlled by the AGC, automatic gain control, so which will be presented later. So let me run it. Oh yeah, so this one's a little bit quick. So I'm gonna start. So I'm gonna start with the output because I know that so the output is gonna be an amplification of the input signal. So this is the output, and this is how it's supposed to be. This is how it's supposed to look like. And we have the input signal. Yes, this is correct. So we have the input signal in blue, and it is amplified, and so we have the output in green. This is the product detector, and so the product detector has two input signal. So the first one is the output of the IF amplifier, and the second one is the output of the beat frequency oscillator. So we are using the SA612 chip for the product detector, and so we have the outputs right here. So based on the data sheet, so this chip function at 9 volts, and since we have to use a single battery of 12 volts, so we had to regulate the voltage in order to have 9 volts, which will be supplied to the voltage, which will be supplied to the product detector. And at the output, so we have the low pass filter, which is gonna let pass only the audio frequency or the message frequency received by the receiver. So this is it, and I'm gonna go ahead and run it. So it's running. Yeah, it's running. So I'm gonna speed up the process. Okay, it just finished running, and it took almost 2 minutes. So I'll go ahead and focus on the most important signals because I know this is gonna again take time. So here we have the outputs of the beat frequency oscillator. So I'm gonna leave that one. So the most important is this one, the output from the IF amplifier. So I'm gonna take this one. So this is it's gonna be the inputs, one of the inputs of the product detector. So we're gonna have this one. So now it's running. So as it's running, so I'm gonna go ahead and take the output of the product detector itself. So it's gonna be right here. So I'm gonna take it as it's running. So yeah, it doesn't allow me to take the output. So I'm gonna wait for a couple of minutes and I'm gonna take the output. But it's looking good. The signal is good. So let me try again. So output, here we go. So now we're gonna have the outputs of the product detector. So we need to wait for the signal to run. So I'm gonna be patient for this time. I'm gonna just wait and see how it's running. So here we go. So this is the output of the product detector, so in blue. And as we can see, so this output is it is the same, but it seems as it was passing to a diode, and this is actually how the product detector behaves. So it's kind of a simple diode. So you have a sinusoidal signal, and then so you're gonna have half of the signal is gonna be passed. And so in this case, we have the bottom signal, which is passed. And so we still have a mixture of the message signal, and we can see it. So the message signal is the one over there at the top, and we also have the carrier frequency, so which is going from 9 volts to 3, as we can see right here. So now, so this is the importance of having now this low pass filter. So this low pass filter is gonna allow to take only the message signal, which is the audio signal, and so this carrier frequency, which has a higher frequency, is not gonna pass through this low pass filter. So now I'm gonna go ahead and take the output from the low pass filter, and then so we're gonna see what we got. So it's gonna take, so it's gonna kind of go again through the beginning, having the input signal. so which is the output signal of the IF amplifier, and then after that, so it's gonna run again for the outputs of the product detector, and then after that, so we're gonna have the final signal, so which is gonna be the audio signal or the message signal that the receiver receive from the antenna. So it's now reading the output from the product detector. So we're gonna wait, and here we go. So that was so quick, the actual signal. So in red, so now we got it. So in red, this is the audio signal. So now, so we have made the complete demodulation of the received signal from the antenna. We went through the RF, we have the mixer and local oscillator, and then we passed through the IF amplifier, and now the product detector. So which is, I mean, one of the most important module in this schematic. So where the demodulation finally occur, and so now we have the audio frequency in red, and so now we can amplify this signal and send it to the speaker, and then now we can hear the message. So this is really cool, and I really like this signal. So it's amazing. Yeah, so in all, this is the product detector, and then we have pretty much everything for this schematic. So this is the bit frequency oscillator, which is pretty much the same as the local oscillator. So yeah, as the same with the local oscillator, I'm not gonna spend too much time on this one. So we have the tank right here, so which give us the frequency, the resonance frequency of oscillation, and so this is the output. So I'm gonna run it, and so we're gonna see the output. And so this bit frequency oscillator, so we design it to run at 455, so around 455 kilohertz. So now it's running, so I'll just take the output. Yeah, so the output is looking good. So this is just at the beginning, so it needs to run, and then as time goes on, and then so it's gonna be stable. So the output is looking good. So I can zoom in and see the frequency, or the signal, I mean the signal. So it's looking good. Let me zoom in again. Yeah, it's looking good, and I can see also the frequency spectrum. So yeah, we have good numbers here, so I would think, yeah, sweet. So we have the spectrum, the outputs, and first harmonic, we should be around 450 kilohertz here, and second harmonic, third, and we go down. So this is pretty much about the bit frequency oscillator. So this is the final schematic or final module, the AF amplifier. So as we got the audio signal from the product detector, so we're gonna amplify that audio signal and then send that signal to the speaker, so that we can hear the message received by the receiver. And the speaker in this schematic is this resistor, 8 ohm resistor right here. This is the speaker. So we have the inputs and the outputs, a simple schematic. And so this AF amplifier is a 3 stages amplifier, and so it is supplied by a single voltage supply of 12 volts. So I'm gonna go ahead and and run it. So here we go. Yeah, so it's running quick. Go ahead and measure the input signal. So this is the input signal. So I took the input signal really, so the amplitude, the input signal very small, so that in order for me to make sure that we can deliver at least 100 milliwatt to the speaker. So and if I take the output of the AF amplifier, let me take the output. Yeah, so we can see that it's really amplified the input signal, and this AF amplifier has a voltage gain of about 30 dB. So I've made the calculation for that. And so this was just to make sure that so with a very small amplitude of the input signal, so be able to deliver at least 100 milliwatt to the speaker. And one more thing that I need to talk about is the total harmonic distortion. So based on the project description, so we need to have a total harmonic distortion of less than 5%. So in order to obtain that one, so let me take out the input signal, and I'm gonna work with the output signal. So in order to determine the total harmonic distortion, so I need to have the harmonics. So I need to have the second, third, fourth harmonics and go forth, and then calculate now the total harmonic distortion. So in order to do that, so I need to have the harmonics. So yeah, I have the nice data, so I'm gonna go ahead, and so here we go. So this is the frequency spectrum of the output signal, and we have the first harmonic, second, third, and I may not take this one as fourth. I'll take this one because this should be should be less than the third harmonic. So I'll take this one as fourth, and I'll continue down. So this is the spectrum. So I've made the calculation, and I'm gonna share that. Okay, so this is the calculation of the total harmonic distortion, THD, and so this is the same frequencies spectrum of the output signal, and so we have the first harmonic, second harmonic, third, and I'll take this one as fourth. And I started from the second harmonic, so which is at minus 30 dB, 30 dBc. I'm sorry, yeah, 30 dBc. So if you take the peak right here minus this peak, and yeah, so we're gonna the difference. So is minus 30 dBc. So this is how we calculate the dBc, and then for the third harmonic, and then so we're gonna take this one, the difference between this peak, this peak and that one, and then so we're gonna have minus 46 dBc, and then I took this one as the fourth harmonic. So then I'll take this peak right here, and then so the difference between that one and this one, so we're gonna have minus 52 dBc, and I'll take 10 to the dBc over 10, and then I made the calculation, and I took the sum of the one that I raised to the 10, so for this column right here, and so this sum I'm gonna take the square root of it, and so I have 0.0321 and multiply by 100, and I get the total harmonic distortion, so which is 3.21%, and which is less than 5% based on the project the description. Thank you so much for listening to this project. It was presented by Daniel Pimbi, students at Texas Tech University in EC department, and this was lab 3 with Dr. Helm. Again, thank you so much.